welcome to the tutorial session. So, in today's tutorial session, we will look at two very important aspects of chemistry, which is thermodynamics and kinetics. So, again these are some concepts that have been done in the past in your previous classes, but we will go over some of these things in some detail, so that we can recap some of the important concepts. So, thermodynamics, as we know, involves basically an equilibrium between, let us say, A and B. So, you have delta G on one coordinate and reaction coordinate is on the x axis, right. So, this is the fundamental aspect of equilibrium, and kinetics deals with basically the height of this barrier, which is delta G double dagger or activation energy. So, with this broad sort of picture, let us look at some specific examples. So, the first example that we will look at is dimethyl formamide. So, dimethyl formamide, whose structure is shown here, has 7 hydrogens as shown here, and one of the hydrogens belongs to an aldehyde or a carbonyl, and the other hydrogens are attached to 2 methyl groups, which is again in turn attached to a nitrogen. So, fundamentally the chemical properties or the properties of these hydrogens would be different. That is, these 6 hydrogens would be identical and this hydrogen would be different. So, if we were to measure an NMR spectrum of a proton, which is basically hydrogen, which is again a concept that you guys have looked at previously, theoretically, since these hydrogens are identical, what you would expect is that you will see one signal, which is shown here, of 6 hydrogens each. So, if you integrate this, you get 6 hydrogens, and if you integrate this, you get 1 hydrogen. So, this is what I would expect as a theoretical NMR spectrum. So, as you already know from basic NMR spectroscopy, that the area under the curve is proportional to the number of hydrogens. So, it is a very simple situation, right. However, in practice, if you record this NMR spectrum, you get a single peak here which integrates to 1, but actually you get 2 peaks here which integrates to 3 hydrogens each. Okay. So, just to recap, the structure that we are dealing with here is N CH3 CH3 C double bond O H. So, the 2 methyl groups which we were thinking as identical are actually showing up as 2 separate peaks in the NMR spectrum. So, this suggests that the 2 methyl groups are actually not the same, right. So, how do we understand this? So, what we know from the prior lectures on amide is that the lone pair on the nitrogen can delocalize into the carbonyl. So, once this happens, it generates a form of nitrogen where there is a positive charge on nitrogen, there is a double bond, right, and a O minus. So, together what it does is that it makes for a resonance hybrid. So, once you have this molecule, there could be restricted rotation around the carbon nitrogen bond. There is substantial double bond character of the carbon nitrogen bond, which contributes to restricted rotation, right. So, therefore, with this restricted rotation, the 2 methyl groups actually appear different, because you have this carbon, this hydrogen here, which is right next to to the O minus, whereas this hydrogen here is next to a aldehydic hydrogen. So, the chemical environment around and the magnetic environment around the hydrogen is actually different, and so you start seeing those differences in the NMR spectrum. But in order to understand this, let us look at some stereochemical aspects. So, if you have this lone pair, instead of going here and instead of looking at dimethyl formamide, we are going to look at another amide just for a basic understanding. So, now in this case you have NH and NH, and these 2 hydrogens are again going to experience a very different chemical environment. But when you have a functional group R attached to it, you actually have two isomers which are trans and cis, and they are going to be in equilibrium with one another. So, if I have to look through one of these nitrogen carbon bonds, then it would look in the following way. So, if you draw the Newman projection, so then the R is on top, that is this, the hydrogen is on the bottom, and this carbonyl is going to be at 90 degrees from the RNH plane, and this R group is also going to be 90 degrees because it is over here, right. So, now if I rotate this and if you go to the other conformer, other isomer, you will get the trans group. So, if I have to draw an equilibrium, then what we would draw out is a structure such as this and this. Here on top must be a high energy configuration or a high energy conformation. There is going to be very little overlap of the orbitals. So, if we start with the two hydrogens instead, we can imagine that both the forms are going to be energetically identical, but there would still be a form wherein there is going to be least conjugation between the two groups. So, therefore, rotation of the carbon nitrogen bond can be understood to be restricted, and therefore, there are two methyl groups that appear and they are appearing to be different. This is an example of how we can understand equilibria. So, equilibria means that they are interconvertible, okay, which means that the barrier of A going to B is not so high that it is not accessible, right. So, this barrier, that is the forward barrier, and the reverse barrier. So, this is delta G double dagger forward and this is delta G double dagger reverse. So, delta G double dagger forward and delta G double dagger reverse are both accessible. Okay. If they are not, if one of them is not accessible at room temperature, then the population would move towards that particular conformation and it would not revert. So, when we observe an equilibrium, it is quite likely or it is important for us to understand that both the barriers, that is the forward barrier as well as the reverse barrier, are both accessible, and then the equilibrium constant would be dependent on the stability of the particular species that is involved in equilibrium. Now, if we look at kinetics, we can draw an energy profile which we have seen in several examples previously. So, you have a reactant going to product, and you can also have a situation where the reactant and product are situated like this, and you have a very small barrier that is separating the two. You can also have a situation where the reactant and product have a very high energy gap between the two, right. So, these heights of these barriers, as we have seen here, will determine what the rate of the reaction is, or in other words, the rate of the reaction is dependent on the heights of the barrier, and this is defined by the Arrhenius equation, which is shown here, which is K is A into e power minus E A by R T. E A is defined as activation energy or the energy required for the reactant to cross the barrier to give you the product. So, there is a situation here on top wherein there is a very high energy species that is produced, which we call as transition state, and then it collapses to give you the product. So, now here is a table that shows you the various parameters, and we will look at this in some detail now.